Hello everyone, my name is Shayok Nag and today I'll be presenting our work Conformal Prediction and MLLM aided uncertainty quantification in scene graph generation. Scene graph generation aims to detect all objects in a scene and recognize their pairwise relationships, also called predicates. The atomic unit of a scene graph is called a subject predicate object triplet, which is as shown in the second figure. Existing scene graph generation methods faces several challenges, such as the long tail distribution of the relationships or predicates, scene descriptions or annotations which are often imprecise or incomplete, and finally the failure of object detection itself. Given these limitations, it becomes critical to quantify the uncertainty of existing scene graph generation models. Our goal in this paper is to achieve the uncertainty quantification in a post hoc manner with probable statistical guarantees. To this end, we leverage conformal prediction. A brief overview of conformal prediction. Given any dataset split into training, calibration, and testing sets, under the assumption of exchangeability, conformal prediction allows us to construct prediction sets, here denoted as C hat. These sets capture the true level with a desired coverage level given by 1 minus alpha. Here alpha is the user-defined miscoverage rate. For a more granular coverage guarantee, class conditional conformal prediction is leveraged, extending the provable coverage guarantee to the individual classes itself, ensuring high confidence for each specific class prediction. Alpha y here can be set differently for each class. Conformal prediction hence provides a statistical rigorous post hoc approach for uncertainty quantification of any underlying classifier. To address the issue of long tail class distribution in scene graph datasets, we leverage class conditional conformal prediction in our work. The calibration, or also known as conformal calibration, involves the usage of a non-conformity measure, here denoted as A. Using the non-conformity measure, we quantify how unusual a sample's prediction is, and we do it for all the samples in the calibration dataset. These scores are then sorted to find the appropriate class-wise threshold denoted by the 1 minus alphath quantile. These are also known as conformal quantile values. We apply the concept of conformal prediction on the object and predicate classification units of any scene graph generation model. This also results in the generation of multiple possible triplets and consequently multiple possible scene graphs in each image. It can be viewed from this figure where we show the difference between standard scene graph generation and our proposed conformal scene graph generation, where in the latter we can see that we can obtain sets or prediction sets of triplets itself. Here we go over the framework. The overall framework is named Plausibility Ensured Conformal Scene Graph Generation, or PCSGG. Starting on the left, given a test image, we use a standard scene graph generation model to extract candidate object and predicate predictions. Using class-wise conformal quantiles for objects and predicates, which are computed using the calibration set, we construct prediction sets for both the objects and the predicate in the test image. These sets are then combined to produce multiple possible triplets between each pairwise objects. We refer to this as a triplet prediction set, and we obtain such sets for all possible triplets in a scene. However, not all triplets are equally meaningful. For example, in the given image, you can see some of the triplets in the triplet prediction set are hand covered in boat and girl holding boat. Now, the first description is implausible from a practical linguistic or semantic perspective, while the second one does not correlate to the actual scene in the image and is hence visually implausible. To compress the triplet prediction set into the most plausible scene descriptions, we devise a multimodal large language model or MLLM based post processing strategy. The final output is a truncated prediction set of the triplets that maintains statistical guarantees while improving interpretability and relevance. Here we go over the MLLM based post processing strategy. We use a one-shot in-context learning approach in a multiple choice question answering or MCQA format for the post-processing setup itself. A system prompt first defines the task, instructing the model to evaluate the plausibility of visual scene graphs based on an image. A one-shot example prompt is provided to help the model understand the expected structure of responses. This example is obtained from the calibration set. The prompt consists of a vision part, which is the portion of the image described by a triplet cropped using the union bounding box of the two objects inside that triplet, and a language part which describes the MCQA format with 5 possible triplet descriptions. The MLLM is constrained to answer just the letter of the option corresponding to the most plausible choice. At inference for any given test image, the conformal scene graph generation based triplet prediction set is divided into further subsets of 5 possible options in the form of triplet descriptions. Each of these subsets are then used to construct the MCQA language prompt, which along with the vision portion or the vision part of the prompt is provided to the MLLM for processing. The output of the MLLM is the option that is the most plausible choice among the 5 that is being shown to the MLLM itself. Now, using the token likelihood scores, we threshold these 5 choices and select the ones that are the most plausible with respect to the given visual context. This process compresses the original larger prediction set down to the most plausible triplets, improving interpretability and practical usability. The threshold is chosen in such a manner that the compression operation does not impact the overall empirical coverage itself. For our work, the MLLM used is the blip2 flan T5XL. Now let's look at the theoretical guarantees behind the scene graph generation in the conformal setting. From theorem 1, we can show that any given triplet can be defined by a class comprised of its subject, predicate, and object classes. The theoretical coverage probability of a triplet prediction set is equal to the product of the individual conformal coverage probabilities of the prediction sets corresponding to the object and the predicate itself. Now, following from theorem 1, we have corollary 1, which simplifies this result, showing that the probability of the ground truth triplet being included in the triplet prediction set is at least the product of the user-defined coverage rates of the object and predicate classes. This formalizes the statistical reliability of our approach, ensuring that our prediction sets provide meaningful guarantees. Here we go over the quantitative results of our proposed method. We choose the individual miscoverage rates of the object and the predicate classes, that is alpha O and alpha R, to be 0.05 and 0.01 respectively, such that the theoretical coverage of a triplet, that is 1 minus alpha O into 1 minus alpha R, is approximately close to 90%. That means with a 90% probability or a confidence, we'd want the ground truth triplet to be included in the triplet prediction set. We then applied PCSGG in a post hoc manner over 5 state-of-the-art scene graph generation methods to quantify their individual uncertainty and check their reliability. The dataset used is Visual Genome 150, composed of 150 object and 50 predicate classes. For the object and the predicate prediction sets, we individually measure empirical coverage called COV. The average class-wise gap in empirical coverage from the theoretical guarantee itself is denoted as COV gap, And of course, we have the average size of the prediction sets itself. Finally, for the entire triplet, we define a specialized empirical coverage metric called CovT to check if the triplet prediction sets cover the ground truth triplet itself. And all of these metrics are shown in table 1, that is the table on the top left corner. And we can see that overall SQUAT and BGNN achieve the highest coverage for the individual objects and the predicates itself, and overall for the triplets itself, showing that they are among the least uncertain, having higher reliability overall across all the 5 state-of-the-art models. In the table below, we compare performance of how the average set size of the triplets itself changes with and without the MLLM based plausibility assessment. And we can see that we have a significant compression of these sets when we apply our MLLM based post processing strategy. And we are able to achieve this with minimal impact to the empirical coverage of the triplet prediction set itself. In the final table, we introduce the metrics coverage recall at K and coverage mean recall at K. These metrics are specific to conformal SGG and are variations of the recall at K and mean recall at K metrics used in standard SGG. Since conformal SGG results in sets of triplet predictions compared to a single prediction, we introduce these metrics for better understanding of how conformal SGG functions with the incorporation of PC-SGG. We can observe from the table itself that applying BGNN with PC-SGG results in the best performance. And from the figure on the top right, we can observe that incorporating PC-SGG with BGNN increases the ability to detect the 5 least observed predicates in the training set itself. The overall triplet empirical coverage or CovT values shows that it is approximately close to the product of the empirical coverage of the object and the predicate prediction sets. Therefore, this validates theorem 1. However, overall, none of the methods achieve the theoretical coverage of the triplets that was shown in corollary 1. This showcases the high predictive uncertainty of the existing models and also sheds light on possible distribution shifts in the train and test splits of given scene graph datasets that make the computation of well-calibrated conformal quantiles very challenging under exchangeability assumptions. The following is a qualitative example of PC-SGG applied over the BGNN model. We can observe multiple plausible triplets and correspondingly multiple plausible scene graphs that can be constructed using PC-SGG. Thank you for listening to my presentation, and if you have any questions, please feel free to reach out during the poster session.